Hello and welcome to a new video in a course on linear algebra. In the previous video, we introduced the definition of vector spaces and we proved that R2 is a vector space. So in this video, I plan to review briefly what we discussed in the last video, and then I'll be going over more examples of vector spaces. So these examples are kind of nice to keep in mind because they keep reminding you of the definitions, but we'll be seeing more examples as we go in the course. So let us do some warm up here and recall what we did last time. So we define a vector space, right? We define a vector space. We said that usually we start with a set, right? For example, let's take the set R2 just as a recap. We start with the set R2, for example, is the set of tuples AB such that A and B are in R, right? Are real numbers. R is the set of real numbers, right? So we start with this as a set. So this is a set of things, set of mathematical objects. And then what we do is that we equip we equip the set that we have with a plus, with addition, and with scalar multiplication. The addition means if I give you two vectors, I remind you that elements of vector spaces are called vectors, right? So if I give you two vectors, for example, AB and CD, you should know how to add these, right? You are defining what the positive sign means. For example, in R, you are defining 2 plus 2 to be 4. You're defining this plus to be as such. In another set, for example, in R2, you have to tell me, or you have to define what the positive sign means. And we said that one way to define it for R2 is to do it element-wise. Like you add the first to the first, and the second component to the second, and in this case you have A plus B and C plus D. And then we talked, so this is the notion of vector addition, right? So we want to define what it means to add two vectors. And we mentioned that the first, so I'm going to write these down, the first important property to check when proving a candidate is a vector space. Okay, so let me just say important properties, because these are three, right? So the first one of these is the closure under addition. So what do I mean by that? I mean that if you take two vectors in the vector space, right? If you add these two by the addition that you defined, for example, in this case, if you add these two in this way, you should get a vector that is still in the same vector space, and this is the notion of closure under addition. So what does that mean? It means that if you for example, if you look at these vectors, when you added these, you get a vector that is still in R2 because this is still in R and this is still in R. Right, and we said that the other important property, so along with this, there comes another property, which is the closure under scalar multiplication. So the second thing we need to define for a vector space is the scalar multiplication, which means you want to take a real number, right? You take a number, I stress it's a number, and you take a vector in V, in this case in R2, right? And you need to define what it means to take R times V. Now vectors in R2 takes the form AB, where A and B are real numbers. So we said one way to define what R times AB is to define this element-wise, meaning you multiply the first by the first and the second by the second. And this gave RA, RB. So the other property that we mentioned it's important to check is closure under scalar multiplication. So you also want, when you multiply a vector of your vector space by a real number, you want also to get a vector in the same vector space. So if you notice here, this is a real number, this is a real number, thus this is in this set, right? So so we also need closure under scalar multiplication. So we took a set, we equipped it with two operations, addition and scalar multiplication, and we require the closure. So this is the first property, right? So now that we have these, now that we have the addition and the scalar multiplication, it remains to check some axioms to prove that a vector, that a candidate of being a vector space is a vector space. So these are quite many properties, but I mentioned that two of these usually need to be checked, and the rest are kind of they hold usually, but they still need to be checked. But you should start with proving two of these that are important, and the rest are kind of just a routine check that turns out to be true in most of the cases. So the axioms are these 8 axioms, and I'll keep it for you to read over these, but I want to remind you of the two that I said these are the important ones to start checking, because these will determine whether or not a candidate is or is not a vector space. So the first one is the existence of a 0, and by 0 here, it's not the real number 0. It's an element of the vector space. It's an element of the set that you have, that you're calling it a 0 if it satisfies the property that when you add it to any other vector, when you add the 0 to any other vector, it gives you a vector. It gives you the same vector. So please be careful here. The addition is not defined for vectors in your vector space and real numbers. You can't tell me I'm adding a vector v to 2. What do you mean? I mean, if this vector space is, say, R2, then then the v takes the form AB. So what do you mean? What would one mean by saying that I'm adding AB to 2, right? That just doesn't make much of a sense, right? So so please be careful when we talk about addition. We're adding two vectors, right? We're not adding scalar and a vector, for example. So as the 0 is a vector, and it has the property that when you add it to any other vector, it gives you the vector back. For example, in R2, we said that the element or the vector 0, 0 is the 0 in R2, because if you add any other vector to it, you get the first plus the first, which is still the first, and the b plus the second, which is still b. So you get the same vector, and that's why 0, 0 is the vector in R2, if we define the operations element-wise. So the second property that we said that it's important to check is that the inverse, the existence of inverse. So what do I mean by that? I mean, if you start with any vector in your vector space, you should find another vector, and I stress here this is another vector omega, and we still haven't defined what it means to subtract two vectors. We just defined what it means to add two vectors. And in this property, we require that for every vector in your vector space to have another vector where if you add these two, if you add v to omega, you get 0. So it's kind of an additive inverse, right? So it's called an additive inverse to it. So I mentioned to you that, for example, in R2, every element AB has an inverse. What's the inverse of AB? What's something that when you add it to any element AB, you get so if you start with any element AB, what's the inverse of that would give you the 0 of R2? What's the 0 of R2? Well, it's 0, 0. What's the inverse? Well, intuitively, you would think I need to cancel the first, so I'll put negative A here, and I'll need to cancel the second, so I'll put a negative B. So in R2, there does exist an inverse for every element in the vector space. So the other properties are usually easier to check, and they still need to be checked when proving a vector space, but they're kind of usually true, right? So this is what it takes to for a set to be a vector space, and I remind you, we proved that R2 is a vector space when we define it as such. I'll keep these for you to go over and remind yourselves of what we did in last video. And then we're gonna go to talk about more examples. So we're gonna start with other sets other than R2. We're gonna define what it means to add two vectors and what it means to multiply a vector by a number, and then we're gonna check whether the properties holds, right? So let me just, before doing that, let me just, because I wanted to list things here. So the important properties that are usually important to check at the beginning to prove a candidate is a vector space are: first, the closure under the addition and scalar multiplication. Second, you would need to check property 3, and you would need to check property 4. So these are this and this, right? So keeping this in mind, let us take another example of a vector space and prove that it's a vector space. So this is what we did for R2, and this is the other example that we're getting, example 2. So just intuitively, just as we considered R2, we may consider Rn. So what is Rn as a set? Rn as a set, it's an n tuple. So you take A1, A2, and so on up to An, where Ai, like A sub any index, is a real number, right? Each and every one of these is a real number. So for example, R3, it has the element, so this means belong, right? So it has the element 1, 2, 3. So this is an R2 because it's a tuple, it's a 3 tuple, and it's kind of contains real numbers, right? So why is R2 a vector space? So for you to be able to say whether or not Rn, is a vector space, you have to define in what sense you mean that. Like, you have to define what are the addition and multiplication. So the addition and multiplication and scalar multiplication, you have to define these, and then your question becomes legitimate of whether or not this is a vector space. So how will you define addition in Rn? Well, you do it similarly, just as you did in R2, right? So to define addition, what you do is you add the first to the first, the second to the second, and so on. So you get this vector. And how would you define a scalar multiplication? How would you multiply a real number by a vector in Rn? Well, you can define it also element-wise by multiplying the first by the first, the second by the second, and so on. And you get this vector. So since we're proving that Rn is a vector space, let's remind ourselves that the first thing that we need to check is that closure under addition and scalar multiplication is true. So what is closure under? So let us see, is it true that closure under addition happens? So if you start with any vector, it's important that you keep in mind that we're starting with any vector. When we prove a property, we don't prove it for a particular vector. We don't prove that closure in R3, for example, is true because 1, 2, 3 plus 0, 0, 1 is equal to 1, 2, in this case 4, which is also in R3, and thus closure under addition is true. No, you don't do that. This is an example. When you want to prove something, you prove it for any element of the vector space. You start with any vector, like you write it in its general form, and you write another vector in its general form, and you tell what it means to add these vectors. Well, this is what it means. This is what the addition is. And is this resultant still in Rn? Well, sure it is, because each and every one of these is still in R, is still a real number, and thus the whole thing is still a vector in Rn. So closure is okay. Closure under addition is okay, is checked. What's the closure under scalar multiplication? Is it true? Well, of course it is, because similarly, if you start with any, I stress, any real number, you don't check it, for example, for R equals 2. You check it for any, like you do the proof in a more general way. So if you start with any real number and any vector, and you multiply these, you get a vector of this form, and hence this is still in Rn, because each and every one of these are in R, right? Each and every one of these is still a real number. So with that said, we just checked the first important thing to check when proving a vector space, which is closure. Remember, there are three important things to start by checking when proving something is a vector space. The second property that we said it's important to check was that the additive zero, or the existence of a zero in the vector space. So is there a zero in Rn? So the next question is there a zero vector in Rn? What do you think? Well, in R2, we said that if we're defining the operation by element-wise, the zero is indeed there, and it's the element 0, 0, right? Is there an element that acts like zero? And by acts like zero, I mean you take any vector and you add it to that zero, and you should get the vector back. Is there an element where if we add any vector in Rn to zero to this vector, we get v back? Well, what does it mean to have any vector in Rn? Well, the vector has the form x1, x2 through xn, and you want to add it to something else, right? You want to add it to something else that gives you back x1, x2, and so on up to xn. And intuitively, you would think, well, it's like if you take all zeros, like if you take the vector of the tuple of all zeros, you still get the same vector, and hence this is the zero in Rn, right? So we just gave the second property, which is the existence of a zero in Rn. So what's the third property? The third property, it would take a little bit more space, so let me just clean things up here. Right. So the third property, which is the additive inverse, meaning, so additive inverse. So meaning you want to start with any vector in Rn, I stress any vector in Rn, and you want to find an inverse of it, meaning if you add it to another thing, you need to get zero. So, and be careful, when we say you need to get zero, we mean the zero of Rn that we just defined. We don't mean the zero as a real number, because you can't add two vectors and get a real number. You get a vector when you add two vectors. So additive inverse in this case, so we start with any element, right, in Rn. When writing proofs, please write details, like say we start with any element in Rn, right, and you write this. So you write words, you just don't write things as such, okay? So so you start with any element in Rn, and you want to add it to something else, so that once you do that, you get the zero vector. So what is that vector? So remember, this is the zero that we just defined to be the zero of Rn. So what is the vector that when added to any vector, like if you fix any vector, what's the vector that when you add it to it, you get a zero back? Well, again, intuitively, you would think that you should cancel the first and the second and so on. So what we're going to do is that we're going to take negative the first, negative the second, and so on, negative the last one. So this is going to be the inverse of the vector that you have, right? So this is it. I mean, you just check the important properties, the important axioms of that usually tells you whether or not a candidate is a vector space, and the rest of the properties I'm gonna leave them for you as an exercise, because they're just easy checks, and you can refer to my discussion on R2 to see that to see the proofs in details, like in written words, in the previous video. So this completes the first example, and Rn, when equipped with the element-wise addition and scalar multiplication, is indeed a vector space. All right. So the next thing that we need to check is, or the next example that we need to discuss is the space of continuous functions. So what do we mean by that? So I remind you, when we talked about vector spaces, we started by saying that we start with any set. So when we say vectors, we don't mean vectors in the just as in R2. So the vector in R2 is thought of this arrow, right? But when we say vector in linear algebra, what we mean is that it's an element of a set that satisfies the property of the vector space, right? So for example, continuous functions, they form a vector space. The space of continuous function actually forms a vector space. How do we see that? So let us define what's the set that we're talking about. C of R, it's defined to be the space of functions. So f from R to R, from the real numbers to the real numbers, such that f is continuous, right? So this is a function, and this is the space of continuous functions. So this is the space of continuous functions. So so as you see here, the vector that we're talking about is a function. So the vector is now a function. It's no longer a tuple. It's no longer a real number, just as in R, or R2, or Rn. So again, to prove that something is a vector space, we have a set of things. What we're gonna do is we're gonna define what addition is and what scalar multiplication is, and then we ask a legitimate question of whether or not that set, when equipped with these addition and multiplication and scalar multiplication, is or is not a vector space. So how would you define addition of two functions, right? So by addition of two functions, I mean, like, you take a function f and a function g in the space of continuous functions, right? And you want to tell me what is the function f plus g? Like, what is this function? You need to tell me what this plus means, right? So to tell me what a function is, you need to tell me what the function is at every x. Like, if I tell you what f of x is at every x, I would be telling you what the function is. Similarly, this function, if we call it h, the f plus g, if we call it h, for me to tell you what h is, I need to tell you what is h at every x, at every real number in this case. So if I tell you what h is at every x, then I'll be telling you what this sum is. So this is what I'm gonna do. I'm gonna tell you, if you take the function h and evaluate it at x, what you do in this case, you do a trivial thing, you do the obvious, you do what you think you should do, and you define the function as such. You evaluate the first function at x, and you evaluate the second function at x, right? I guess for you to see what I mean here, let me give you an example, right? So let me give you an example over here. So let's take f from R to R and g from R to R, real number to real number, and let's define f of x to be x, and let's define g of x to be cosine x, for example. And now these f and g are elements in the space of continuous functions, are vectors there. And I'm asking you, what is f plus g? Well, to tell me what f plus g is, or how you're defining this plus, you need to tell me what f plus g at any x is. So f plus g at any x, right? We're defining this to be f at the first x, like the first function at x plus the second function at x. And what is that? Well, this is f of x is x and g of x is cosine of x. So this is x plus cosine x, right? So this is how we're defining the addition of functions. You take what the function, how the function is defined, and how the second function is defined, and you add these, right? And next we need to define what scalar multiplication is. So so let me just clean things up here, and let's define what scalar multiplication is. So how would you, if you start with a function in the space of continuous functions, and you take a real number in R, for example, let's say 2, right? I want to know what 2f means, right? What does 2f mean, right? For example, if we start with f, a function that is continuous, let's say f of x equals to x, we're asking what is 2f as an element of the space of continuous functions. For you to know what 2f is, you have to know what 2f evaluated at every x is. How would you define 2f as a function evaluated at x? Well, there's a trivial way of doing that, which is that you take 2 and you multiply it by f evaluated at x, right? So so this is one way, and this is one way of defining what scalar multiplication is, or how you want scalar multiplication to be. So so this is the general definition, right? So now that we defined what scalar multiplication is and what the addition is, the vector addition is, the next thing to ask is whether closure happens or not, right? So the first question is closure, because we're proving that this is a vector space. We're proving that CR, the space of continuous functions, is a vector space. So let us see. So do we have closure under addition and scalar multiplication? So let's see if that's true. So we're starting with any element f, any element in CR f, and any element in CRG, and when we're adding these, we're getting something else of this form. But you know, like when you add two functions, you get a function, right? Yeah, like it's obvious. And when you add two continuous functions, you know also that you get a continuous functions. So so the addition will take two continuous functions, add them, and still give you a continuous function, and thus closure under addition is correct. And similarly for scalar multiplication, if you take a continuous function f, right, and you multiply it by a number, we're defining it as such. But we know, for example, if f of x is continuous, right, and g of x, which is 2x, like which is in this case 2 times f of x, right? So we know that when we multiply a function by a scalar, we still get a function, and this function is still continuous. Closure under scalar multiplication is also evident. So the next thing to try here, the next thing to check here is what's so-called additive identity. In other words, the zero. Is there a zero in R? Is there a zero vector in CR? Is there a vector? Is there a function, in other words, because what are vectors here? These are functions. Is there a function which when I add it to any other function, I get zero? That's the question. Well, of course there is, because if you take the zero function, what is the zero function? You take, we're defining it as O, let's say. So the zero function at x, we define this to be zero for every x. So if we define this for zero to be 0 for every x, then if you take any other function, for example, if you take f in R from R to R, then what is f plus 0 at x, right? So remember, this addition is an addition between two vectors. So we don't know yet that f plus 0 is 0. We're trying to prove that. Okay, so what is f plus 0? Well, you go to the definition. It's the same as f at x plus the function 0 at x. But this is the same as f of x plus the function 0 at any number is 0. But 0 plus f of x is f of x. And thus, this thing is equal to f, right? And which means that f plus the 0 vector is equal to f, and thus this 0 that we just defined is a 0 in the vector space, and thus the vector space has an additive identity, as we claimed. So what's the next thing to check? Well, the next thing to check is the property of the existence of inverses. So let us check if that's true. Let me clean these up and we're gonna check that. So let's check the additive inverse. So how do we check if additive inverses exist? We start with any function f. Let's take f from R to R, and we want an inverse to f, meaning we want a function g such that when we add f to g, we get the 0 function, right? So what is the 0 function? The 0 function is a function which, when evaluated at x, it gives 0 for every x, right? So so what would you think f plus g at x might be, so that what do you think g might be, so that if we add these two, which we define this to be f of x plus g of x, this is gonna be 0 for every x. Well, one typical way of one obvious way of defining this is by defining g to be minus f of x. So what we're gonna do is we're gonna define g to be minus f. In other words, it's minus 1 times f. So it's minus 1 times f, right? Because f is a vector, I can multiply it by a real number, right? Because when I multiply it by a real number, this is how scalar multiplication happens, right? So minus 1 times f is the same as, at x, is the same as minus 1 times f of x. In which case, these two will cancel over here, and you'll be getting 0. So we just also checked that the inverse exists for every element of the space of continuous functions. So with that said, we checked the important properties that have to be checked for a candidate to be proven a vector space, and I'm gonna also leave the rest of the properties for you to practice and prove these. So this is the second example. And similarly, one can do other spaces. For example, the space of polynomials, and you can define these similarly, because remember, polynomials are just functions, right? So polynomials are just continuous functions, and the same that we proved for the space of continuous functions as such, we can prove for the space of polynomials as such, and you just define again the addition to be element wise. As such, you add the coefficients of the corresponding power of x, and you do scalar multiplication also, quote unquote, element wise, and you see that the same properties will also hold trivially, just as we proved for the case of space of continuous functions. So you see, now you have at your pocket examples of vector spaces, namely you have Rn for every n, and you have the space of continuous functions, and you have the space of polynomials. So now polynomials are called vectors because the space of polynomials is a vector space, and we're gonna talk more about the more examples later. But before we wrap up this video, let me give you an example. Let me give you a non-example, something that is not a vector space. So let us see what's a non-example, right? The set of integers. So if you take the set of integers z, which is 1, 2, 3, 4. So let me say plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, and so on. So you take all the integers with 0, of course, and you ask the question, is this a vector space? So when you try to prove something is or is not a vector space, the first thing you do is that so the addition in Z is known for you. Like you just add numbers in the usual sense and you multiply numbers in the usual sense. So the first thing you do in your mind is you try to check the three properties in your mind and you see which one of these would fail, because if you can find one of the properties that fails, then the set can't be a vector space. So you start running things in your mind and you look for Z. For example, the first property, if we want to prove Z is a vector space, now Z is not a vector space over R. So if you want to prove Z is a vector space, we will have to check closure under addition and scalar multiplication. Now addition, it seems that when we add any two elements of these, like we still get an integer, right? If we add 4 and 9, we still get an integer. You ask the next question, is it closed under scalar multiplication? If we take a real number R, right, real number R, and you take any integer n, right, is it true that R times n is still in the set, which means is it still in Z? Is it still an integer? Well, that's not true. And when you want to prove that something is not a vector space, meaning you want to prove that one property is not true, you provide what's so-called a counterexample, right? So you provide a counterexample. So when proving things, you prove things. So when proving something is a vector space, you prove it in the very generality. You prove that the property holds for any element of the vector space. However, when you want to disprove something, you want to disprove that one of the properties is true. And how do you disprove this? You disprove this by giving an example. So disproving is easier, while proving is harder. Right? So disproving, you only need to give a counterexample in this case, and let's see. For example, if I take 2.3, right? So this is a real number, right? This is a real number, and I take an integer. So let's put these between brackets, and I multiply this, say, by the integer 5. Let's say 2 for simplicity. So this is an integer. And this is a real number. However, when I multiply these, what do I get? I get 4.6. Now, 4.6 is not an integer. This is not an integer. This is not an integer in this set, right? So since we just multiplied a real number by an integer, and we got something that is not an integer, thus we don't have closure under scalar multiplication, and thus this cannot be a vector space over R. So Z is not a vector space over R. I hope that this is clear. And there are more examples that we're gonna go over. I'm gonna leave this a bit harder example for later, but let me just give you a more simpler example here. The more simpler example is R take away 0. I might have talked of this before. So if you consider the real numbers and you omit 0 out of it, is this a vector space over R? Over R? Well, no. Why? Because there is no 0 vector, right? So if you take any real number, for example, if you take 2 in this case, remember when disproving something, you only need to give a counterexample. If you take 2, there's nothing that you can add to 2 and still get 2. Why? Because we omitted 0 from this set. There is no 0 anymore. Like any number that you add it to 2, whatever it is, it's not gonna be 2, right? So so if you add it to any number n, this is gonna be 2 plus n. This is not 0. This cannot be 2, right? This cannot be 2 unless n is 0. But there's no 0 in this set, right? So this set is also not a vector space. So in the next video, we'll be discussing the notion of subspaces, and we'll be giving more examples of vector spaces.